Right. So let's now talk about rotational kinematic and the variables that we require. So I've already mentioned that theta is important. Okay. So, and we'll soon see that it is in 1:1 correspondence with x in one dimension. So we know what theta is. In the example of the scale, it was the angle with the x-axis. Now I need to introduce one more terminology before we go ahead, and that's important in the context of this chapter. The two examples that I gave you last time of a scale and a tire are called fixed axis rotation. It's a terminology that confuses me sometime. Um, it does confuse me sometime, um, and I guess you will get confused in the beginning. So fixed axis, remember the examples. Fixed axis rotation. Remember the examples of a scale and the tire. Okay. The what I mean by fixed axis is z-axis. Okay, the axis is parallel to the z-axis. It's not z-axis, and that's the confusing part. Okay, so for example, let's take the tire for example. So it's rotating now about this axis. At this instant, it is rotating about this axis, which is passing through the center, but it's perpendicular to the board. That means it's parallel to the z-axis. Well, it's not the z-axis. Z-axis is somewhere here. If this is x and this is y, then the z-axis is here. So the axis is parallel to the z-axis. Okay, so you got to remember this. And that's called fixed axis. Well, it's not actually fixed. You can see that the axis is moving, and therein lies the confusion. So then, what's the other? The other rotation that will be important for us is called pure rotation. Okay, and funnily enough, pure rotation is the rotation where the axis is actually fixed. I mean, it sounds like a joke. Okay, so in this case, it's not parallel to z-axis, it is the z-axis. Okay, so I'll give you the example of pure rotation. So let's forget about everything else and talk about pure rotation. Now pure rotation is quite easy to understand because it's a simpler form of rotation, which is that the axis is now fixed. I mean truly fixed. So here's the my standard example. Now you have a scale. Okay, so permit me the joke that I use every year, which is let's crucify the scale now. I mean you could do it here or here or here, wherever you feel like, but then once it's crucified here, it can't move from there. Okay, and now you rotate the scale. First of all, the this point can't move. Okay, this point can't move. Now I think the important part of this example is that in this particular example, it's nothing to do with it is not the center of mass. The point can be anything, and it could be the center of mass also. Nobody to stop you from choosing the center of mass to crucify it, but you could just do it anywhere. Now once you but by the way, only one point. Okay, now once you fix that one point, fixed, okay, the point is fixed, it can rotate about that point, and it can go all the way round and round. So this motion is pure rotation. Okay, so I used a scale, but you could just rotate any object. For example, I mean anything, any object. For example, a hoop. Okay, now you could fix this point here. It's a hoop. Okay, and okay, and then about this point you can rotate it. and rotate it and rotate it. So this is an example of a pure rotation. Now you don't have to choose that point for rotation. You could choose any point. um, for example, if this does have, let's say, some crossbars, you could choose this point if you want, about which it's going to rotate, fix that point, or this point, or basically I think you must have understood that it can rotate about that point or this point or anything. Okay, now important point really is that it's okay, that axis, okay, the axis in pure rotation can be chosen to be the z-axis. By definition, let's just always choose that as the z-axis. So which means that the object moves in the xy plane. And also what it means is that z-axis is truly fixed, whatever that means. And this is not fixed, I mean, it's not called fixed axis rotation, it's called pure rotation. Okay, so let's take the example of a scale. Let's not okay, so here's the x-axis, here's the y-axis, and here's the scale, and the scale has been, let's say, crucified here at the origin, and I've chosen that as the z-axis. So that's the axis of pure rotation. And now we're in business. We can tell where the scale is by telling you what is theta. So this is the telling you the rotation. Okay, this theta, and then it just keeps on rotating like this. So it'll have a different theta at a different time. Let's call it theta whatever 2, theta 1 at a different time, t2, different time, t1. So now you can tell me the position of the scale. This example of pure rotation is the key example. It holds the key to the final problem, believe me. And here's the good news, it's really easy actually. Now 3 or 4 simple keys hold the solution to the whole problem, and that's what I meant by a systematic presentation. So here you go. The pure rotation just requires me to tell you theta. Now this is very similar to telling me in one dimension motion what is x as a function of time. So here's the 1-1 correspondence. So theta tells me the position of the scale, x tells me the position of the particle. So see the commonality position. Okay, so now the question is, does x change? Yes, it does. Does theta change? Yes, it does. Well, if theta changes, then I would like to know the rate at which it changes. Okay, just a small quick clarification. So if suppose the angle theta is pi, well, you know what it means. And then suppose you tell me it's 3 pi by 2, I think I know what it means. If it's 2 pi, it's come back to its original position, but that's not the way I want to think about it. I'll just say that it completed 1 revolution. And if it's completed 1 revolution and let's say come here, then add pi by 2 to 2 pi and tell me. That way I know that it's completed 1 and 1/4 revolution. So for example here, then you will tell me it's 3 pi. So I know that it is 1 whole revolution and another half revolution. Okay, so please remember this. You don't tell me in multiples. Just don't tell me a value between 0 and 2 pi. You're right in the sense that that will tell me where the object is, but the information that gets hidden is, has it reached there after already traveling 1 or 2 revolutions? So it's better that you tell me the total theta. So let's say 5 pi. So I know that it is 2.5 revolutions. Okay, so keep that in mind when we talk about theta. So let's summarize. You tell me what is x, and I know where the particle is. You tell me what is theta, and I know where the body is in pure rotation. Great. Awesome. Okay, and then you tell me that, well, x is changing. I notice that x is changing. I notice that theta is changing. What do I try to focus my attention on? The next kinematic variable, which is x is equal to dx by dt is equal to delta x by delta t is equal to velocity is equal to limit as delta t tends to 0. So here is a person who might become important very soon. Well, you can do the same thing here, and it does turn out the same thing. The same story turns out to be true. It turns out to be important, and it's a simple matter to calculate d theta by dt and understand the significance of this rate of change of theta with respect to time, and then you write it in the similar way: limit as delta t tends to 0, delta theta over delta time, and then we got to give it a name. In this case, let's call it omega. Okay, so this has a unit of meter per second. This has a unit. Now I told you last time that think in angles in terms of radians, so radians per second. And omega is omega is just a name. So omega tells me, oh yeah, it's a function of time, tells me that at that instant what is the rate of change of theta. And well, what did we do here next? We just went ahead and said, look, what is the acceleration? Okay, why are we defining all this? I think you know the answer, but let's write it anyway: dvx by dt. Okay, and the same old thing: limit delta t tends to 0, delta v by delta t. And why are we doing this? Because it's connected to the law, which is F is equal to ma. What is this law for a particle? Okay, so particle motion. So let's do one thing. Let's see it. Let's just go one step ahead and follow the same thing. And this time, I'm going to calculate d omega by dt, which is equal to limit as delta t tends to 0, delta omega by delta t, and this has a unit of meter per second square. This has a unit of radians per second square. Not a surprise at all. And this again has to be given a name. We could call it alpha t, and this is called, well, this is called acceleration. This is called what's it called? Okay, rotational acceleration. I forgot. My goodness, I've forgotten. This should be rotational acceleration. Okay, so alpha is rotational acceleration. Okay, I don't know what's the correct word. Usually, when you just call alpha as d omega by dt. That's the way that's the way people talk about it. Alpha is the rate of change of angular velocity. Okay, so rotational acceleration. Okay, so now do I stop here? Yes, the answer is yes. Okay, just run out of space, but is there an equivalent of this in a law of nature? The answer is yes, and it looks like this. Right now you don't worry too much about it. What each of these terms means is what we're going to get into soon, but what I'll tell you is that I think I should tell you that I is fixed value for the object once the scale is crucified. That means once the axis is fixed. Okay, so once the axis is fixed, I becomes a constant. In other words, I can change if you change the axis, and that's what I mean by the shape of the object is going to play a role. Okay, but don't worry about it. At this stage, what you need to realize is I depends on the shape and but it is fixed once the axis is fixed. Now, so this is like mass, and then alpha is exactly what we just calculated, and tau is okay, I think this is a bad way to write it. I should write it as tau. Tau is okay. Should I write it as tau z, because we are mostly worried about rotation about the z-axis? Okay, so in this example, and alpha is exactly what we discussed, angle with the x-axis. So tau z, which is a torque about the z-axis, is going to I alpha, is going to be the law. Okay, and there's no worries about laws. Laws are experimentally discovered formulae. And now the story is the same. The law enables us to calculate torque. Once you know the torque, you calculate alpha. Once you know alpha, you're in business. You do the same old thing again. You come backwards from alpha to omega, and then from omega to theta, and the backward journey is okay. The forward journey is calculus, the backward journey is integration. So that's what I meant by the same story. Now, one more time, we remember that, okay, just to remind you, a is equal to constant is a important case, much similar to that alpha, the rotational acceleration, is equal to constant, is an important subcase which runs completely parallel to this, which is hardly a surprise because all the definitions are completely parallel, but it is good to summarize nicely with the correct notations. And this, I think, has been done in practically every good book, but here we do it here very nicely. So you say, look, F is equal to ma. Why? Because God built it that way. And then here we say tau z. Basically, we're talking about pure rotation. In pure rotation, tau z, which is the torque about the z-axis, is equal to I times alpha, where alpha is the angle with the x-axis, and I depends on the axis of rotation. And this is true because God made it that way. It's a law of physics. Okay, and tau is equal to I alpha. Now we make use of the law because this has been verified experimentally. There never seems to be any contradiction. We are good with this. Now what this means is that if you give me the external forces, then I can calculate torque, I can calculate the external force, I can calculate alpha. Now once you know alpha, you happen to know what alpha is. It's dvx by dt. Now you know what alpha is. It's d omega t by dt. Now let's assume it's a constant. Let's assume it's a constant. It's not a constant usually. I mean, if it's not a constant, it will be a function of time, but let's assume it's a constant. If it's not a constant, then I can write Vx is equal to u plus at. And if somebody asks me why, I'll say, look, differentiate it. That's it, we're done. Now I'm going to say that I can go backwards and say omega final is equal to omega initial, which is, see the 1-1 correspondence with this formula. You can almost predict it. Okay, plus alpha t. And somebody says, hello, why is this true? Well, you know now what to say. Differentiate it, and it turns out that it'll satisfy this. Great. So this is the initial velocity, this is the initial angular velocity. Oh my god, I think this is a new things we learned, so better highlight it. Omega is called, okay, I think it's important, angular velocity. I think that you should always write the unit just to make sure that, okay, alpha is Oh, angular acceleration, not rotational acceleration. Okay, which is equal to radians per second square. And now you go backwards one last time and say x final minus x initial, and you know what x final means, you know what x initial means. The position of the particle is ut plus half at square, and the reason is of course that if you differentiate this you get this, so you can easily now predict the rotational kinematics formula that you need. Theta, okay, just highlight this. This is something that we must not have highlighted enough. Okay, and write it in exactly the same way. You know what theta initial is. It's the initial angle that the scale makes with the x-axis. You know what theta final is. It tells us the angle with the x-axis, but also gives us information of how many rotations have happened. Now this is equal to omega initial time, okay, because omega initial corresponds to u, plus half at square. Oh, there you go. Horrible mistake. Alpha t square. How could I miss this? Okay, plus alpha t square, and then all of this is true for the same reason that if you differentiate this, you will get this. Okay, so here you go. This is not a challenge to remember these equations, and but I highlight that don't go around making a rampant use of this without checking that a is equal to constant and alpha is equal to constant. So please be careful. Make sure you make this check before you use these formulae. But in the reverse, when alpha is constant and when a is constant, you don't use this formula. That would be, yeah, that would be unfortunate. Okay, so that's it. We have finished rotational kinematics. I'm in a state to start the long journey of rotational dynamics, and it's a slightly long journey, but we had to get done with this. In the next class I shall discuss about it's important that I mention what's the next upload on. It's based on now we're coming to the big thing, which is rotational dynamics. But before we enter into this, we need to arm ourselves with a little bit more math. So in work energy, we needed something called the vector dot product. Okay, and it comes naturally in defining work. Okay, so we have talked about work, but we can just define the vector dot product to be work. And once we define the vector dot product to be work, we can understand what is the mathematical interpretation of this so-called dot product. See, the thing is, why would you not simply call dot product as work? Because the dot product is useful in other situations as well. And it's better to study it as a math entity, which is a dot product, which is nothing but, I mean, the work gives us motivation to define something called a vector dot product. It's useful in other situations. Now we need to define something called a vector cross product before we jump into the study of rotational dynamics. But one thing I can tell you, cross product, okay, vector cross product. One thing I can tell you quickly is that this math that we learn when I explain this, I'll get back to this and then get to this. The math that we learn helps us to, I think this point I want to highlight before we get into this. So what is the advantage of all the math that we learn here? That's the cross product, dot product. First of all, it may be useful in more situations, but I think that's not the most important thing in this present situation that we are in. in our case, it makes the laws statement very compact. I think not just that, it makes the calculations easy. Okay, so if you sort of learn the, how should I put it, rules of dot and cross, then the calculations become, I may use the word a little, sort of, it becomes like a series of steps where, because you're following the rules, you don't make mistakes. Okay, so this helps you to do a complicated calculation in a algorithmic way, systematic way, and in the process, because you are very familiar with these rules of the game, you don't make mistakes. So basically the calculations can get messy, and your best chance to avoid the mess is to learn these rules, and suddenly it becomes very compact and very neat, and that's the solution to avoid the mess. So if you are not following these wonderful rules, you might still get the correct answer, but it might be a little messy, lengthier, and not only do you take more time, but you might make a mistake. In this case, it becomes compact and neat. So to summarize this, it's a great computational tool in a subject where things are a little messy, but the entire mess is given a miss by using the correct tools, and you'll start appreciating that these tools are wonderful, and more importantly, they were discovered by people, I mean clever people, who worked with these problems before us, and in the process discovered the right, in fact made the right tools. So really, what I want you to remember is that the vectors and the rules of so-called dot and cross are um, are not physics, but calculation aids, which you will love to appreciate because they make life so easy and simple for yourself. And not surprising that K&K are like fans of vectors from day one. Okay, from the first chapter, there's too much emphasis on vectors. And just to remind you again that K&K use bold letters for vectors. Okay, they don't call a vector A as like this. The A itself will be in bold, and that's how you're supposed to recognize a vector in K&K. So please be careful here. Whenever you come across a bold letter, it might be a vector. It is mostly a vector. So keep that in mind. And now we are also ready to jump onto the bandwagon, because now we're going to get more and more comfortable with vectors, and therefore we can jump on to K&K's bandwagon. And believe me, the journey with K&K is going to be quite spectacular, but it'll take some time, meaning that I don't expect you to be champions in this immediately, but by the time, let's say, you get to 12th, if you're firmly in control of these methods, you're going to reap the benefits really nicely. Okay, so this will be my next class where I'm going to talk about dot products and cross products, but I think I've given you the motivation of why we're going to go through it very slowly. Alright,